Okay, good morning. So welcome everybody. Uh, yeah, we're near to the end. So it's like the final sprint. Yeah. The audience is getting bigger and bigger, so this is great. Yeah. So this is something to be expected. Anyway, so I think it's time to wrap up a little bit and bring us to the sort of contemporary research in LLM. So first question, what is LLM? Large language models. So everything is like LLM, large language models, GPT-2, and blah, blah, blah. What makes the models large? That's a great question. So when the model starts to be large, do we have like small language models and large language models? Well, maybe we do. So what makes a model large? Any idea? It's the number of parameters. But when do you say like, well, the number of parameters is large, so I can call it large language models?
I know modern ones have 7 billion.
Yeah, so it's very arbitrary decision, let's put it like that. So you make a great big model, 7 billion parameters, and you put large language model. 5 years ago, large language models was something with 1 million parameters. Now it's like small. So the world is changing, and just upfront, a lot of the terminology we'll be talking about, it's a made-up terminology. Somebody came up with these terms, and everybody either adopted them or called them differently, or just change their meaning. So for example, LLM is one term, large language models. There's people calling them foundational models. These are people mostly from Stanford. They call them foundational models because they founded an institute for research in foundational models. So this is the name they put it, the label. So it's a lot about labeling things. Some labels basically stick around and everybody's using them. Some are kind of arbitrary. So large language model is something which is large, many parameters, billions. Okay, cool. This is a large language model. So this is what we were talking. So today it will be not really deep down in things, but more like a high level, and talking about more contemporary stuff in large language models. Because so far everything you need to know about large language models you know already. Because yesterday you built GPT-2. I mean inference, not learning, but basically that's it. I mean if you know encoder and decoder, you are up to date with the models that are used nowadays as large language models. Okay, so now that you know the encoder transformer, so we spent 1.5 or maybe even 2 lectures on BERT, the encoder transformer, and we spent a lecture on the decoder transformer, which is the GPT. They both come from one single paper, and I keep repeating this sentence, attention is all you need, because it's the title of this first paper who actually introduced the transformer back in 2017. So attention is all you need. It's actually a nice title of a paper because it sticks around. So attention, because attention is the core of these transformer models. So yeah, 2017, and we're gonna spend a little bit of some time talking about the origins of these transformer models in this architecture, in this original paper of attention all you need. But basically now you know all the blocks you need to work with. So I didn't start with this first paper because the model looks more complicated if you see it for the first time. But if you know the encoder and if you know the decoder, then you just stick them together basically and everything will work out more or less. Okay, so that's what we're gonna do today. But just to recap, so what's the difference between an encoder transformer and a decoder transformer? So what's the same? What's the similarities in them? So transformer is, when we talked about it yesterday as well, what is transformer? So there's attention and all the stuff going in, learning contextualized word embeddings for each token. There is one big difference in the attention between the encoder and the decoder. And there's so many similarities in there. If you remember yesterday, we did some operation which prevents leaking data from the future to the past. What was that? It was masking, exactly, it was a masking. So we're setting the mask, and where do we set the mask? In the encoder or in the decoder? Yeah, say loud. Not really, in the decoder. Because the encoder, as we have, so remember BERT, what was BERT about? BERT took the whole sentence, and for each token in the sentence, learned a token embedding, which took into account all the other words in the sequence. So in BERT, we were basically removing one word and BERT was pre-trained on this mask language model where you have a sentence, take one word, mask it, and then try to predict the missing word back. So you look on the left and on the right, which means you can look in the future in BERT. Basically, you take the whole sequence and just take everything and learn the missing word. So there's no masking required. While in GPT, in the decoder, we use language modeling. So what is language modeling doing? What do you do in language models? What is language modeling about? Any idea? What is language model good for? No? No? What is language model good for?
Because get the condition probability of a token
Mhm.
based on features.
Yeah, exactly. So exactly. You want to learn, given a couple of tokens, the history, what is the next token? Predict the next, basically, language model is predict the next word, which is expressed as conditional probability over the vocabulary, given the context, what is the probability of the next word? Exactly. So this is the decoder thing. Decoder is trained as language model, which means we always need to look only into the past, because we're generating the first token. And when we generate the next token, we can only see the first token because we don't see the future. There is nothing to be generated. There's nothing in the future. So then we take the 2 tokens, 3 tokens, 4 tokens, and that's it. That's where the mask is. Okay, so this is the main difference. It's fundamental difference in conceptually how the encoder works and how the decoder works. Okay, so this is the masking. Any questions? More or less makes sense for now, right? I mean, okay, cool. We talk about it. So this is what you see in the original paper as a transformer. Okay, this is the transformer encoder-decoder. It looks complicated and scary, but it's not, because you know it already. We've seen everything here already. We spent at least 3 lectures and a couple of exercises on talking about this. So let's have a look what's in there. What do we know already? So we have some input embedding. So we have some inputs. Okay, here the depiction is not from left to right, but from bottom to top. So, people draw things differently and they have different meanings, so be aware of that. But you should understand now every piece of this block already. So let's have a look what's in there. So we have inputs, and for each input, so these inputs are, what are the inputs? What was the inputs yesterday? No. No, even before that, you have a sequence of tokens. What do you count? What is coming to the network? The token IDs, exactly. So we have a list of token IDs. So these are token IDs, and we turn them into input embeddings. And we have 2 embeddings basically here, 2 types of embeddings for the input. So for each token, we have the embedding of the token, but we have also another embedding. What was the? Oh, okay, here. So here's the answer. It's positional encoding. So we have for each position, we have its own embedding. So position 1 has a embedding, position 2 has a embedding, because in attention, the attention block is what was a fancy term? Permutation invariant. So if you shuffle the words, you get the same result more or less, basically, in the attention if you don't encode the position of the tokens in there. So this is how it works. So we have positional encoding and the input embedding and sum them up together. Okay, good. So that's what we did yesterday in the exercise. And then we have these N transformer blocks. So they are stacked on top of each other. Okay, so we saw it before. Okay, so this is one of these blocks. There is this thing called multi-head attention, and there's a couple of other things, the normalization, layer normalization. So we had before again, and we have also like a feed forward. So this is something we've seen before in all 3 lectures. And the core part here is the multi-head attention. Okay, so what are these 3 arrows here in multi-head attention? Why are there 3 arrows in this multi-head attention? So we have the input coming in. Let's call it X, because why not? It's just what people use for X. So this is the input, and now we have the input split into 3, and it goes into the block called multi-head attention. So why do we have 3 arrows? What can they mean? Because there are 3 things going into self-attention. Yeah, exactly. We have the query, we have the key, and we have the value. So query, key, and value. So what are these query key and values? How did we get them? How do we get the query key and value? Remember? No.
We took the input, we call it X, and
Yeah.
we multiplied with 3 different matrices to protect it linearly.
So we take it X and multiply by sub W 4Q. Okay, so this is special, and then maybe some bias, whatever. Okay. Oh, okay, that's true. Okay, so we basically there's a projection of each input through some matrix, and these matrices are learned, and they are different for Q, key, and value, but they're roughly the same. So some projection. Okay, good. So we have this multi-head attention, query key, and value. So what is the most important part in this self-attention? What was that? So the self-attention is just as we saw yesterday, it's a one line. It's a one line of Python code. So what was that? How did we do this? There was this dot product between each token in key and each token in query. So we took how was that? We took I guess the query matrix. So this is a matrix of, okay. This important part is that the length or the size of this matrix is the length of the input. So this is in times some dimensionality of the attention. Okay, so each row, or in the X actually, in the X, each row corresponds to one token, right? I mean, this is just repeating. We spent some time on that with very, very detailed in the previous lecture. So if you want to refresh that, just go back and rewatch it again if you want, or look at the slides. Anyway, so we have this Q, this query matrix, and then when we took I guess the keys, right? How was that? Keys, and we multiply them together. There was some other operation. I'm missing something here. What do I need to do? I cannot just multiply these matrices because they have the same thing. So what if I need a dot product of every row with every row from the other? I need to do this thing. I need to transpose the other matrix, right? So this is taking each row from the first matrix and multiply with each row from the other matrix. This is it. This is the dot product for each row. It's just expressed as a multiplying two matrices and one is transposed. But we're, transposing matrices has a meaning in linear algebra. This is not it. We're just doing dot product because the dot product gives you some strength of similarity. This is the core meaning. Dot product is some sort of raw similarity or some association, strength of associations, let's put it like that. And that's what we're doing. Okay, so then we did some scaling, something like that. Then we have the masking. Oh, no, here we didn't have the masking. The masking was here in the decoder. So in the encoder, we just have this through softmax, and we multiply that by the B. So this is a matrix multiplication, right? Yeah, so this is the attention. This is what this is the add symbol, matmul. Does it make sense? All good? Any questions? So we multiply this by this. I mean, I'm using the Python operation which we had yesterday, so multiplication, but it should be just maybe like a dot. So this was the part of the single head attention block, and we have multiple of them and stack over a couple of layers. So this was the encoder. This was BERT. Okay. Any questions? You don't have to write it down because it's everything in the previous slides. I'm just repeating it for we know where we are. So any questions? All right. So then we have the other part, which is the decoder. And well, we are talking about decoder, which was a little bit simpler than here. So in our decoder, again, we had the input. So what was the input to the decoder? What is the input to the decoder? Any ideas? It won't be any different from the encoder. So it's just token IDs, right? We have the previous token IDs, and we want to generate the next token ID. That's it. Input, output. Token IDs in, next token ID out. Then we add it again to the input, list of token IDs, next token, and so on. Autoregressive is the word, okay? So we have token IDs, and again, we have positional embedding. So there's no difference. Then we have multi-head attention, but it was masked. Okay, so here's the mask. Here's the causal mask. We spent quite some time last lecture on that, and yesterday as well. We showed the matrices, how exactly the masking works, and in this attention. Excuse me, yeah, in this attention head basically. So the masking comes here into play. So again, we have 3 arrows means basically query, key, and value. So there's the same scale dot product, but then we're adding here the mask. Okay, right? We're adding here the mask. And what was the mask doing again?
That's the upper diagonal of the matrix to -20 or very small value in practical computation event looking ahead.
Yeah, exactly. So it says somewhere in the matrix, and why I'm saying somewhere in the matrix, it depends if you look like rows, columns, or column rows, because it differs. You can have like tokens could be the first token, second token, third token, or you can build it like, oh, first token, second token, and so on, which kind of shifts your mask. So the mask has to have a meaning in your context. But in our context, we have each row is a token. So row, row, row. So what's coming out of here is in times in matrix, which means the number of tokens times number of tokens, because we created dot product of every combination. So for example, if we have 3 tokens, let's do 5. 5 tokens in, this is 5 times 5 matrix. And then, so here, and would look like something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, okay, 5 times 5 is big. But anyway, so this would be a matrix. And as you just said, we're masking the upper triangle, which means, what does it mean? If let's say I'm at position 3 now, so token number 3, and I want to attend to the previous tokens, which of those I have to mask out? I'm at position 3, and I want to put mask here on this row because I don't want to look into the future. So what needs to be sort of erased?
I'm at position 3, that means I know the first, second, and third
Yeah.
token, and I want to know the fourth, so I can know.
So I have to cancel this, and I have to cancel this. Yeah, exactly. And canceling near masking means we're plugging something, some value, which after you squeeze it through softmax will give you 0. So what do you need to plug in softmax to give you 0? What is softmax? So the first question, like, what is softmax? What is softmax? Well, okay. You must know what is softmax, okay? So if you don't know what is softmax, I'm sorry. So the softmax is some function which is exponentiation of the input over normalized. So in softmax, there is exp of something. What do you need to plug in to exp of something to get 0 on the outputs, okay? What is it? So you have exp of something, and you want to get 0. What this something has to be? Yeah. Infinity. Okay, so that's a good candidate. How does exp function look like? Something like that. So what happens if you plug in infinity? What you get? Yeah, what you get? No, what you get? I mean, if you plug in infinity, what you get from exp of infinity? What is it? Infinity. Okay, so that's not a good candidate anymore. So what do you need to plug in? Oh, minus infinity. What happens if you plug in minus infinity? Yes, you get 0. So it has to be minus infinity. Okay, cool. So which means we're basically replacing those with something which is minus infinity. So which means on position 3 is minus infinity here. Position 2 is going to be those will be minus infinities, minus infinities. So this is the upper triangle matrix. As I said, if you have this transpose, you have to kind of pay attention to the details. So if you're just masking things without thinking, then things will go wrong. And as we saw yesterday, the minus infinity is a very nasty thing depending on the implementation. So if you use PyTorch, minus infinity might work. If you use NumPy, it will break. So we're here in the decoder, we're masking, and what else? And the rest is the same. So we have softmax over that. and multiply by the V. So this is the same thing. And this is the only difference between encoder and decoder. Attention, so attention block in encoder and decoder, because in decoder we want to do the masking, the causal masking, not to leak information from the future, because we use it for generating the next token. Okay? Does it make sense now? Cool. So this was the first part of the decoder. Yeah, and we had this normalization, we had this, what does it mean to add here? So add here, which means, for example, that x becomes x plus attention of x. So right, I mean, we have x is coming here to attention, and it's also added here. So this is the add operation. It has a name. You remember the name? Oops, single L, residual connection. Okay, so it's not so important, but it has a name. So that's why the add is here. So now you understand. I mean, the idea is like if you see the transformer here, you understand everything because it's possible, because we talk about it, you know. So this is the residual connection. Okay, so and then there's this feed forward and basically the same part. Now, these two blocks, encoder and decoder, we talk about them. They were single kind of like not single. There were self-alone blocks. So there's no connection between. We didn't have an encoder decoder architecture yet. This is what they propose: encoder decoder. So both things together, and how they connect those things together is through something called a cross attention. Wow. Okay. What is this? Well, conceptually, you want, if you're, let's say you do machine translation, okay? So there's an input sentence, and they actually did machine translation with this architecture. I'll show you later. They have the input sentence, which is in a bunch of tokens, and each token has a embedding, right? This is the input. Then you start generating your output, token by token, and at each point, you not only want to see what you generated before, you also want to attend to the whole input. You want to see which token is important where. So if you remember LSTM with attention, where we were looking at LSTM with attention, in the decoder, we are looking to every token in the input and find the attention weight. This is the same thing. In every step of the decoder, we want to look not only on the, on the decoder part, but also on the full input sequence. So this is where we take cross attention. So here, so this is the decoder part, this is the X coming in, and now the Q, the query, key, and value are not coming from the same input, but the value, excuse me, the query and key are coming from the encoder. Okay. So here, this is the query, this is the key, and they are coming from the output of the encoder. That's why it's called cross attention. How does it work? So here, let's say we would have. I'm running out of space now. Well, anyway, let's try. So in the cross attention, excuse me, cross attention. So the Q and key are from encoder, and the value is from the decoder. So, and the rest is just the same as before. There's a multiplication of some weights and multiplication of some, just the same thing, the same thing, but the input to this attention head is coming from both sides, from the encoder and the decoder. And the rest just works as we had before. Okay? So you learn at every step how to project all the input tokens, or excuse me, all the encoder tokens, how to project them in some Q and K, and then do the dot product and blah, 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 blah. All the stuff keeps the same. But you just take the queries and keys from from the other part of the transformer, from the encoder. So this is not like self-attention. In self-attention, you have everything here from the same input. In self-attention, this is self-attention. X times something, X times something, and X times something gives you Q, key, and V. While here in the cross-attention, the query and key are coming from other part of the model, and the value is coming from the other part of the model as well. This is the cross-attention in a nutshell. Any questions? Does it make sense? Could you implement it theoretically? Theoretically, yes. I mean, theoretically, there's nothing to prevent you to implement it because you just take the X from somewhere else. It's at the end of the day, this is a computational graph. Remember, everything is a computational graph. Everything is direct acyclic graph, and you will run backpropagation on the whole thing. It's big, it's complicated, but it's still a graph. So, you know, all these arrows means like, well, there's information flowing from one block to another block, which means you can do here like a backpropagation to the weights here and backpropagation here to the weights. Everything will work just out of box as we had before. There's no conceptual difference. We're just sticking two sort of architectural blocks together, but that's it. Okay, so this is the encoder-decoder. Yeah, and then the rest is feed forward as before, and linear and softmax projecting the tokens. We had it before. So this is the decoder, the right-hand side, and this is the encoder left-hand side. This would be BERT, this would be GPT, and the original attentionist only paper had encoder-decoder architecture, where you had the cross-attention, so to basically transfer all the information from the entire input to the decoder. Is it better than just BERT? Is it better than GPT? It depends. So, but just so, okay. Any questions? I mean, is it clear like why encoder-decoder? It's complicated because this is more weights, but the only difference is like there's two blocks, the encoder, which can see the whole sequence at once because there is self-attention. The decoder sees the whole sequence at once, but there is masking because we don't want to, leak tokens from the future. And how they interact with each other is the cross-attention because the decoder can look all the time into the encoder. Yeah, because why? If you translate a sentence, I want to go home. I don't know, some other sentence like English to German. There's maybe some examples. I don't have any examples. But anyway, I want to go home. Ich will nach Hause gehen. So you can see, I want to go home. You can see the tokens all the time when you're generating the next token because you've seen this as an input. So this is it. Okay. Good. That's it. So attention is all you need. This is the game changer. This is the paper. So what they did. Okay, here's again. This is quoted from the paper actually, and what I describe it. I mean, we talk about it, but let me just rephrase it again. So maybe there's more information in here. So the transform uses multi-head attention in 3 different ways. Okay, multi-head attention. So we know what is attention. We know why it's multi-head because we have several attentions in parallel. Okay, so we know everything. Multi-head attention in 3 different ways. The encoder-decoder attention. Oh, okay. So encoder attention. The queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. Oh, okay. Maybe I made an error here. I'm sorry. Okay. Maybe I made an error. So here, what they're saying here that from the encoder comes the keys and values, not the query. Keys and values, and the query is coming from the decoder. So I'm sorry. Yeah, that's a mistake. So queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. So we have, sorry, it's clarified now. Well, I mean, I just mess up the Q, K, and V. But this is the cross attention also. Cross attention is a term people are using as well. So this allows every position in decoder to attend over all positions in the input sequence. Exactly, that's what we said. This mimics the typical encoder-decoder attention mechanism in sequence-to-sequence models. Yes, because that's what we saw in, for example, LSTM or RNN with attention. That's the same principle. You want to attend to every single token in the input, and you want to see what's the importance of every input at each decoding step. Okay, so this is the cross-attention again, quoted from the paper. And then this is a recap of the other self-attention. So the encoder contains self-attention layers. Okay, so we know exactly what self-attention is. In self-attention layer, all keys, values, and queries come from the same place. Yes, exactly. Everything is dx times q. The q is x times w, key is x times w, and v is x times w, and these have different weights. And the output of the previous layer in the encoder. Each position in the encoder can attend to all position in the previous layer of the encoder. Okay, good. So this is the bird thing, like every token sees everything. Okay, good. And the third one, similar self-attention layers in the decoder allow each position in the decoder to attend all the position in the decoder up to and including that position. Yeah, this is the excuse me. This is the masking thing. So you can really see only the previous tokens and this one, but not the future. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. Autoregressive is like you eating your own input. We implement this inside of scale.product attention by masking out, setting to -infinity, all values in the input of the softmax, which corresponds to illegal connections. So this is like looking into the future. Cool. Now you understand the paper. This is from the paper, by the way. This is verbatim quoted from the paper, which you now understand exactly what I mean by that. Well, was it easy to understand it from the paper at the beginning? Well, not for everybody, not really. So it's kind of like it took some effort for the community kind of to understand all these little details, what actually it means, look at the implementation, and then just understand all the mechanics. And as I showed a couple of lectures before, like if you look into the original Vaswani et al. Paper, this is what you see, but there's no formal algorithm describing exactly. There was an implementation, there was this, but it took a couple of years for people to really formalize maybe the algorithms, and that's what we've been using, what we were using in the previous lectures, like the formal methods of transformer, which exactly you see like what are the matrices, what are the parameters, how they come up together, and so on. Okay, so this is what you won't see like formal algorithms in the original paper. You will see something like pictures, nice colors, and maybe a couple of other pictures and descriptions and formulas. But now you should have everything you need to understand this, like not only conceptually, but also in the very, very detail. Like, oh, what are these matrices? What's coming in? What's in there? Okay. So this is the transformer, the original one. And what they used here, they actually did it for machine translation. So WMT 2014 is one of the standard, or used to be one of the standard data sets for machine translations. So you have over 4 million sentence pairs in both languages. So what they use, this is quoted from the paper. So now you will understand everything. So okay, we have data set of sentence pairs. Sentences were encoded using byte pair encoding. Okay, so what is byte pair encoding, by the way? What is byte pair encoding? It's a label for something you know. I mean, we've been using that all the time. We know it under different names, maybe. Well, I think we know byte pair. I think we talked about byte pair encoding, but we talk about other encoding. So what does it mean, byte pair encoding? Sentences were encoded using byte pair. So you have a sentence and you want to turn it into token IDs. You can use byte pair encoding. What is it?
Documentation method that I think first splits the text into characters and then merges.
Yeah, okay, exactly. It's a tokenization, it's just a tokenization method. So it takes a sentence and split it into tokens. And the tokens are, we call subword units. Subword units. And byte pair encoding is just, as you said, like you start with characters and grow. This is one way how you build subword units. This is just one way, and that's what they used because it came out from, actually, byte pair encoding came out from machine translation because you can have a shared vocabulary. So for all your languages, you have the same tokenizer. Why will it work? Well, if you start just with characters and your languages are similar in terms of they're using maybe a Latin alphabet, like English and French, English, German, French, then you have the same vocabulary for English and for French, and you have the same token ID, so it makes things simpler. Anyway, so byte pair encoding is just one way of subword unit encoding. Okay, shared source target vocabulary, 37,000 tokens. Not bad, okay, 40,000 tokens in your vocabulary. Each of them has a token ID, and you just tokenize your sentence, input, output into token IDs. Easy. For English, French, we use the 60 million larger WMD, 36 million sentences, and split tokens into 30,000 word piece vocabulary. I think the word piece is the same as subword units here. I mean, the terminology is kind of, you never know unless you see like the code what they really mean by that. But let's say this is some subword unit tokenizer. So byte pair and word piece may be the same thing. Word piece is basically, I guess, word piece is the name for subword units. It's the same, and the byte pair encoding is how you create it. Okay, any questions? So how you prepare the task for machine translation? You just chunk it into tokens, and that's what you have, encoder-decoder. And what was super interesting back then, like 2017, when they came out with this paper, they trained, so there was no pre-training, like unsupervised pre-training. If you remember BERT is pre-trained on something, and GPT is also pre-trained on something. Remember what is GPT pre-trained on? Yeah, I don't mean like data set, but like how you is there a task how you pre-train your model? You create an artificial task, so the model learns something. In GPT, it's a language modeling task. So what you're gonna do is you predict the next token, right? You take and you might take Reddit, you might take something else like the internet, and you just say, well, my n tokens are the input and the next token is the output, so predict me the next output. And that's how you pre-train the decoder model. BERT was pre-trained a little bit differently. So there were two tasks in BERT. And one was, so you remember what was in BERT? BERT pre-training, yeah. So it's masked language modeling where you mask one word somewhere in the middle or multiple words. So you basically don't take the next word, but something in your sequence. Okay, there's one task. How do you get a data for it? It's easy. I mean, no. I mean, how do you get the data for it? Just to make clear that we understand, you don't need any labeled data. So how do you create data for it? Yeah, just take a text corpus and randomly mask the words. Yeah, no. I mean, this is important because this is how you create your training data for free, unsupervised or self-supervised, because that's what they didn't do. They trained this model only on this task, like on this machine translation. There was no pre-training. It was just supervised learning, input, output, English, German, English, German, English, German, 45 million sentences or how many, I don't know. And they trained the whole model on that. There was no pre-training in the original Vasvani paper, okay? So this would come later in GPT and BERT. The original transformer paper, the transformer architecture, was not pre-trained on something else. It turned out later on that if you pre-train it, wow, it boosts because it learns so many things about language except for just machine translation. But anyway, this was like machine translation. And well, these are blue scores. So the higher the better. What is a blue score? Something like, what is it? Blue score. Yeah.
Blue score is, I think, the n-gram is the precision over the
something like that. It has something to do with the n-grams, and you compare the overlap of your reference translation and what you're producing, what you're translating. So there's some overlap because you can have like multiple reference translations, and you just say like, well, okay, how precise am I with this? With my all n-grams here in the generated text as compared to the reference translation, something like that. Precision-oriented measure for translation. What was the other? The recall-oriented. Remember? Rouge. Yeah, exactly. Blue and rouge. French names for machine translation metrics. I mean, everybody remember that. Okay. Cool. And so they trained two models back then. The base model and the big model. In the paper there's like how many transformer layers and how big, and so big means big and base means small or something like that. As you can see with the large model, you just beat everything what was on the market back then. So typically the bold numbers means like the best result in the table. So what you wanna look for is if you create a new model, you wanna have a table where there is something like our model and everything is bold because you're just much better than the other papers, the other. So I don't know what these are. Some of them are, I don't know, some deep networks, ensemble, whatever, some sort of machine translation systems. And what they did with this transformer model was just beat everything, almost like, okay, here maybe this is sort of similar result, but a blue score, something like +1 or +2, it's a great step actually. So blue score increase in 1 or 2 is really substantial. And they did this with this paper. So they basically created a transformer model and do like machine translation. And back then it was like the best machine translation system. And very cool architecture that nobody really understood until it was adapted by the entire community in the world. Okay. So this is just to show like, yeah, they use machine translation as a task and only this task. They tested this only on machine translation back then. Supervised learning, end-to-end, no pre-training, okay? Later on, we'll see how pre-training works. So, okay, this was the first part. So now you should kind of understand the whole, so, okay. If there is something you should know in 2024 about NLP is the transformer. This is it. It's been here for the last, I don't know, 7 years now. So 7 years, and since the last 7 years, this is the architecture for language, for speech, for video, for images, maybe. Well, images are kind of special because they have some other things, but for NLP, the transformer is the thing. So you should know that. I think it will stick around for a while because it's just such a powerful architecture. For many reasons. So you should know that. I mean, you can forget about LSTM. LSTM is like, yeah, it's a nice concept, recurrent neural networks, but they're just kind of slow and they don't scale. And okay, cool. So you don't want to do that. Transformer, while it scales well, it scales absolutely amazingly. Why? Because it's just multiplication of matrices. This is it. Everything is multiplication of matrices. Query, key, values, multiply matrices. What else? Scaling, multiplying matrices, masking, adding matrices. Everything can be super parallelized because you just multiply matrices together. There is no sequence of steps you need to take as in RNNs. So this is one reason. And others like, yeah, it's just a cool architecture for some reasons. So it's an active area of research, basically why it works so well. Also like, yeah, what's happening in there? Like it's, if you have like a model of 70 billion parameters, what's going on? So, it's a whole new area of research. So this is something you should remember. I mean, you should know the transformer basically, because whatever you do in the future with NLP in the next 10 years, I'm pretty sure it will be the transformer or its derivatives like BERT. Well, BERT is not really, but GPT stuff. This is it. There's no magic in there. This is really interesting. Like you only need one architecture to know, like one algorithm. So the algorithm for training is stochastic gradient descent. It's 5 lines of code. And the architecture you have to know is transformer, and you can get rich. That's it. It's NLP is it's very interesting field because everything is sort of centering now around this one architecture and one way of doing things, and it just works. How it works, you just make it bigger and bigger and bigger. And as we will see, the size matters here. The bigger you make it, the better it works. Everything else is just irrelevant over years. Okay. So we saw the transformer is they use it for machine translation. So this is one task. Maybe you want to do more tasks with transformer. And maybe you don't even want to say specifically or train the model specifically for the task, but you just tell the model, do a task. So this is what people in this T5 paper did. So T5 is encoder-decoder architecture. So now you know encoder-decoder. So this is what we had in the transformer model. And what they propose here, what was super nice about this paper, is they treat every text processing problem as text to text. So taking text as input and producing new text as output, which means this. So there is a model, T5, text to text transfer transformer, whatever it means. It's encoder-decoder. So this is bus one, this is attention all you need. This is the transformer. Transformer. This is just more or less unchanged architecture of the transformer we just saw. Maybe they changed a couple of things, but conceptually it's the same, encoder-decoder. So, and remember, the transformer was trained on just machine translation. So the input to the transformer was that is good, and the output would be that is good. Now here they say no. I want to tell the model what to do, like in language. I want to tell the model translate English to German. That is good, and the output should be that is good. So you're basically instructing the model what to do. The model doesn't know what to do. The model wasn't trained on anything, any specific task, or well, actually it was trained on all of them. So you would prepare your data. If you have machine translation, you would prepare your data where your text, the input text, would not only be like that is good and that's good, but it would be like translate English to German and that is good, that is good. So this is for machine translation. Okay, so this is task number one. Another task, well, let me skip the cola sentence, but let me say STSB sentence one, the rhino grazed on the grass. Sentence two, a rhino is grazing in a field. I think this is semantic text similarity benchmark, STSB. So it's basically measuring how similar two sentences are semantically. What is the meaning of these two sentences? Are they completely, something like, well, not like we had this natural language inference, but it's not the same because inference needs some other knowledge. This is like are they similar or not? So if you see sentence number one, the rhino grazed on the grass, and you see sentence, the rhino is grazing in a field, how much are they similar on some scale? I don't remember the scale, might have been like 1 to 5, I don't know, some number. This is interesting because this is a sort of, this is not a classification task. This is not saying like, oh, positive, negative, or some classes or next token. This is saying a number. You want to predict a number. The way you predict the number here is you predict the text of the number. You predict the, you predict number as tokens, not as a number. You cannot, you just predict token for 3 and dot and 8. It's text. It's not a number. The model doesn't know anything about numbers. You just predict 3.8. It sounds crazy, but it works. It works because the model learns also something about arithmetics and something about numbers and stuff like that. So you would say here STSB. So you're saying, well, STSB is the task. So semantic text similarity benchmark or something like that. Sentence one and sentence two, and the model, and you train on these tasks, right? You show it to the model. You fine tune the model on that. So the model knows if the model sees STSB, it knows, oh, there's two sentences coming, and I should predict a number, which is a similarity, but nothing else. You just instruct the model saying, well, do STSB this and that, or this is the same model. You don't specify, you don't fine tune the model on task one and on task two and task three. You fine tune it on all the tasks at once, and the model will pick up what to do. Another task here is summarization. So for example, you say summarize, and then the input is like state authorities, dispatch emergency, blah, 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 blah. And the summarization should be 6 people hospitalized after a storm in Atala County. So you say, well, yeah, the task is summarize. Do it for me, please. And the model should learn not only to understand what the task is, but to do the task. This is easy. This is text in, text out. So there's no surprise. Text in and numbers out. This is interesting, but it works as well. Yeah. I think this is a cola sentence. The course is jumping well. I guess this is something like the task was grammar checking, I guess. The course or something, meaning checking. The course is jumping well is not acceptable sentence. Something like that. I don't know exactly the task, but something like a classification whether the sentence is acceptable or not. Okay. All these tasks at once. Every task we consider, including translation, question answering, classification, is cast as feeding our model text as input and training it to generate some target text. This allows us to use the same model, the same loss function, the same hyperparameters, and so on across our diverse set of tasks. So we have one single model which can do all of these tasks at once because all of them are just text in, text out. So this was a little bit like a paradigm change because here you do just machine translation. So you show sentence and the sentence. So it knows to do machine translation. Here, it knows all the other tasks, everything. Like you fine tune it on them. Okay? Any questions? Yeah, looks easy now, right? I mean, sure, everybody, back then it's like, really, you want to do? So by the way, if you predict a number, how is it called? Do you know the name for this kind of paradigm? Or we have a classification where we classify in categories. If you predict a number, it has a different name. You know what it is? Yeah, continuous number. Regression, exactly. It's regression. And the crazy idea to cast regression as predicting a token of the value, yeah, I don't know, but it works. This is really like the game changer. Everything is text in, text out. Well, now it seems obvious because everybody's using ChatGPT, so it text in, text out, of course. You ask, well, do me, what is 2 plus 2? And ChatGPT tells you it's 5. What is it doing? It's doing arithmetic somehow, but everything is just tokens. It's text. There is no arithmetics in there. Yeah. No, it's not doing arithmetics. It's just doing, the transformer thing. It's doing query key value, projection, learning. It doesn't know anything. It doesn't know anything about arithmetics as we do, but maybe it does, but we don't know. We don't know we don't know how it works. Let's face it, we don't know how it works. We don't know how it exactly works. We kind of, it's like a big network with 70 billion parameters. I don't know how big. And there are all like attention, 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 attention. Everything is multiplied together, scaling and stuff like that. And you plug in what is 2 plus 2, which are, I don't know, 10 tokens. And then you want to know like how it computes the tokens. Good luck. Well, people are trying to kind of inspect these models. I mean, you can see the models, you can see the weights, you can see everything. This is transparent. But how it internally really works in arithmetics, it's like sort of like a brain research. You plug something in the brain and do stuff like how to, yeah.
It's kind of like the task predict the next word because 2 plus 2 equals, and in most texts it was based on the answer during the before.
That's true. So that's true. If you see it in training data, that's great because you can remember stuff. So these models, they do remember actually stuff from the input, like verbatim. There was a paper last year, well, not last couple of, last month actually. If you ask ChatGPT, repeat this word forever, poem, poem, poem. It starts repeating poem, poem, poem. And then after 100 words poems, it starts spitting out the training data. And it starts spitting out the training data, and in the training data, there's information about people, names, addresses, social security numbers, and stuff like that. It's leaking training data. Okay, cool. Welcome to privacy of large language models. It's hard. So it's remembering training data. You can prevent it. People try, or GitHub Copilot. They built some heuristics in the Copilot to prevent actually repeating, prevent verbatim outputting the training data because they might be copyrighted. Okay, so you were asking for a guest lecture yesterday. I'm gonna do that because this is my research field, like privacy in language. I have cool examples in there, so let's keep it for next time, okay? So anyway, where are we? The arithmetics and stuff like that. So it's a cool, does it do arithmetics? Yeah, it does. It knows things, but not as maybe we think we do. Yeah.
I think just doesn't consider numbers anything different than letters.
How do you know? You don't know. That's the point. We don't know. It might. We don't know. It's really an active area of research. Like how does it represent things and concepts? And there's techniques, how you try to kind of sneak, how you try to interpret things and weights and neurons and layers and attention and things like that. And if you leave something out, how it will change and stuff. So it's really an active area of research to try to understand how these somehow conceptually work. Okay, mechanistically we know how it works exactly. Q, K, V, self-attention. This is just multiplying numbers, but conceptually we don't know exactly. So you might be right, but you might not. Nobody knows. Maybe some people know. I mean, this is not my area of research of interpretation of LLMs, but people are spending an enormous amount of time on doing research on that. Okay. Shall we make a break? And then let me see what I have here. T5. No, okay. Let me finish T5 and then we move on. Okay, so 10 minutes and then we'll move on. What T5 did was not only training on these tasks, but also self-supervised pre-training. And back then, of course, the self-supervised pre-training was known already because this is 2020, so I guess they started 2019. It's 1 year after BERT and GPT, so pre-training was a thing already. They just used the encoder-decoder like original from 2017 paper, but pre-training, self-supervised pre-training was known to be like the way to pre-train the models, the way to start learning something and then to fine-tune. So they tried different types of pre-training here. And the typical would be the prefix language modeling, which means, can you read that? Is it okay? Yeah, it looks small to me. Oh, anyway, sorry. So basically, prefix language modeling means like, oh, finish the sentence. Thank you for invite. So the input would be, thank you for inviting me to your party last week. And here in the prefix language modeling would be, thank you for inviting. And the model should predict me to your party last week. Yeah, okay, this is basically the language modeling thing. Then the BERT style would be masking. So thank you, and you mask 2 words, me to your party. And this is like a corrupting word, so replacing one word randomly, something like that. So this is the BERT style pre-training. And the model should recover what these 2 tokens were and this as well. What else? Drop tokens, random spans, whatever. So some other things. They tried really like a lot of pre-training things, but these 2 two mostly widely spread are just language modeling, which is this one, like finish a sentence, and the BERT mask language modeling was important for BERT encoder. Nowadays, basically, most of that is just language modeling. So this is like, I guess the majority of large language models are using this, just predicting, complete a sentence, basically. So they pre-train it. And the question was, on what, how do you want to pre-train this thing? So what do you want to use for pre-training the thing? So what do you want to use? I mean, if I tell, okay, here's the model, can you pre-train it in self-supervised manner? What do you do? Where do you get your data from? From the internet. Okay, good. Everybody agrees you get the data from the internet. So how do you do it? Okay, here's the internet. It's a thing. Can you get the data from the internet? How do you do it? Like technically. All of them. The more, the better. You use crawlers. Okay, so you want to crawl it by your own? Oh, there is a command crawl. Okay, so has anyone crawled the internet yet? I mean, have you tried to crawl the internet? You know what crawling the internet is? We know what crawling is? You just go to links and download the HTML. Have you tried to do it? Don't try. So I tried it on the I tried to crawl the internet on the university network. And no, I mean, I clarified everything up front. I said like, okay, listen, I'm gonna crawl the internet, and yeah, sure, okay. And but the thing is, if you're on the university network, you have access to things that the rest of the world doesn't have access to. For example, the libraries, the IEEE, and all these kind of libraries where not libraries, like the digital kind of journals and stuff like that. So once you start crawling that, there's terms of conditions which your university is kind of signed up to. You shouldn't be crawling us. So yeah, I got a couple of angry emails from some institutions saying like, well, actually you're crawling our entire library, so stop it. Otherwise, we'll just, we cut you off from the whole library, the whole university. It's like, oh yeah, sorry. So this is not a good idea. So you should, it's possible to crawl the internet, but think twice before doing it. Don't do it. Because there is a common crawl. So commoncrawl.org is a nonprofit organization somewhere in the US, which basically does crawling the internet for you every month since 2011, something like that. The question is like, is it legal or not for them to do? Because they crawl the internet and they put it for free for everybody. So you can download the internet, by the way. If you go to Common Crawl, have you ever worked with AWS, Amazon Web Services? You know what AWS is? Okay. So there is this large storage S3 on AWS where you can store like terabytes, petabytes of data. It's all there. The Common Crawl is on AWS and you can download it. It's a couple of terabytes. Well, back then, 20 terabytes. So you can if you have $1,000 budget, you can run things on the Common Crawl on AWS with MapReduce stuff. You can do it. You can work with the internet. It's just big. So what they did is they took this Common Crawl and removed markup and blah blah blah. So basically, if you have HTML in, you want the text. How do you do that? There's tools, Beautiful Soup, or just whatever, some extraction. The sky's the limit. The problem is the quality of that. Unfortunately, the majority of the resulting text is not natural language. So what is on the internet? Like if you scrape the internet, what is in there? What is the majority? I'm not talking about like videos or porn. I mean, no, this is just text. What would be in there if this is not a text? You'd be surprised. A lot of crap. So, for example, there could be many scrape pages contain warnings stating that JavaScript should be enabled. Yeah, welcome to the internet. If Common Crawl doesn't crawl with JavaScript because JavaScript interpretation is kind of sucks for crawlers, and they're using, I guess, Common Crawl is using Apache Nutch, NUTCH, something like that, which doesn't interpret JavaScript, which means like most of the pages which you crawl will be like, oh, your browser doesn't support JavaScript. So this is what you get. So you need to get rid of that. What else? Some pages that place lorem ipsum. Yeah, of course. If you just design a web page and you have nothing in there, just put lorem ipsum. And there's a lot of such things on the internet, so you have to delete that. Some pages contain code, so curly brackets, so you want to remove code. Unless you're doing something with code. But if you're doing natural language text, you want to get rid of all the code. You want to get rid of, we only retain lines that ended in terminal. Yeah, so they wanted sentences. So something which looks like sentence means it's a line and ends with a period, so that's what you want. If there's a page that has fewer than 5 sentences, maybe you want to get rid of it. So cleaning, basically this is cleaning up the internet. So if you want language data, don't take what's in the Common Crawl. You have to clean it. You want to remove, well, it's a design choice. So maybe you want to have a dirty, nasty, obscene, and bad words. If you don't want them, just remove them. Maybe you want to keep them. It's a design choice, okay? If you're building like a bad chatbot, then you want to keep them, obviously. Or you want to train on 4chan or something like that, so you take the consequences. Whatever you train on will have impact. And this is the point. So the T5 paper, they build this colossal, clean, common crawl corpus, which is quite small. If you take 20 terabytes of 20 terabytes of data and end up with just almost 1 terabyte, you see how much crap is on the internet, so to say. So, and using this, they pre-train the masked language modeling. Okay. So, take-home message, you can work on the internet, but the quality matters. And you have to take measures to improve your models. Here, they use this cleaning. I think GPT-2, and I guess I talked about it, they use the data or only pages which were referenced from Reddit and had like karma 3 points, something like that. So there's some sort of quality check that somebody read the page, it's not completely spam or scam. and maybe there's a text. So you have lots of heuristics. If you just take the internet and throw it in, there's this saying like, how was it? Trash in, trash out. Something like that. Okay. So you wanna the quality matters here, and they show it in this C4 corpus. Okay. And they did like 20 different tasks. So I don't know if you can you read that? Okay. So there's a couple of tasks. So for example, the glue. I guess we talk about glue, and you should know a little bit of glue. So glue is the general language understanding evaluation, which is a couple of different tasks. It's a collection of tasks like natural language inference, semantic similarity maybe, and stuff like that. So this is like one of those complex tasks. And others, semantic text similarity, STST, what is this? Natural language inference, recognizing text entitlement, Vinograd scheme, reasoning, squat, squat, actually we talked about it. Question answering, super glue is glue on steroids, like multilingual, and others. So a couple of tasks. Okay, that's great. And they obviously train a couple of models. They call them wisely T5 small, base, large, larger, and I guess largest, something like that. Like they grow in size here. In terms of parameters, the question was like, what makes it large? It's an arbitrary decision, but maybe you just double the number of attention heads, or double the depth of the how many transformer blocks you're using and stuff like that. What do you see here? What do you see here? No matter what you do, no matter what works best are larger models. The bigger your model is, the better it works. Everything else is like not important. Scaling the model size to 11 billion parameters was the most important ingredient for achieving our best performance. Okay. This is kind of sad, but good at the same time. Like you can have like super many clever things in your architecture. You can change the architecture. You can, I don't know, introduce layer normalization here, GELU versus ReLU, things like that. Like you have thousands of different ways to change your model. At the end of the day, if you can make it bigger and train for longer, you win. It's sad, but that's the reality. If you can train it on the internet, that's great. If you train it on all the crawls from the last 10 years, the better. If you can make it 2 times bigger, the better. That's it. It just grows the capacity and the capabilities. Okay? Does it make sense? Yeah.
How do the models react to using data which is coming again and again, because some text on the internet will be repeating because they are different sources?
So you can duplicate stuff. So that's what you do. Some people do that. They duplicate it. So we discard all but one 3-sentence span occurring more than once in the data set. So you might want to, it's again a design choice. Maybe you want to repeat the same thing over and over, but maybe not. Maybe you want to just have the more diversity.
I think it also show the model in certain things that are true. So if something gets repeated often, it might be
exactly. If you repeat something often, it might be true, but it might be like a complete fake. But if you repeat it often, it works, and the model will pick it up. So yeah, that's that's an open. So you want to deduplicate it. And actually, if I remember correctly, they with one of these large language models, it might have been GPT or it might have been T5, where you actually run through the collection just once, or maybe a couple of times, maybe 2 times. But the data is that big that you can, you run out of your compute power before you just reach the end of your data set, something like that. So that's how you prevent like being duplicates. But the thing with the remembering stuff, as I told, like it remembers training data. It happens even like if it sees like only once. You see the data only once, and it will just save it somehow to the weights. So, okay. So this is the take-home message. The bigger, the better. That's it. More data, bigger architecture, training for longer will fix everything. You can just do like tiny little kind of improvements. But if you have like, I don't know, 1,000 GPUs or 10,000 GPUs, half a year of training and the whole internet, That's the thing. Okay, so let's make a break, and then we talk about the cool stuff in context learning. Any questions so far? Good. Okay, so let's do 7 minutes, okay? So let's move on to the next kind of I would say like approach or a way of working with large language models, and it's called in-context learning. So let's see. So this is taken from I guess from the paper of GPT-3. So 2020 GPT-3 from OpenAI. There was a technical report, quite long, and the title was what was that? Language models are future learners. So what does it mean? So we should kind of decode what does future learners mean and stuff like that. Because it's also like a paradigm shift in how we work with language models. So what do we see before so far? We have the transformer model, which you can train end-to-end on machine translation. Sentence in, sentence out, one task. Then you can pre-train the model on mask language modeling or whatever you want, or just language modeling. You pre-train the model, and then you fine-tune the model on your task. So what is fine-tuning? Well, the same as the end-to-end training. Like you fine-tune it, you just do it for machine translation for one task. You update your weights of the model and stuff like that. Or what we saw with T5 is you have pre-trained model, pre-trained transformer, and then you fine-tune it on multiple tasks together where you say what the task is, like translate this from English to German, or do this and that. But still, we are kind of training the model in terms of fine-tuning. So fine-tuning means basically just training, updating the weights of the model. So forward pass, backpropagation, gradient, update the weights, do it again for the standard supervised training. Okay, does it make sense? Supervised training, fine-tuning is the same thing. And here's again the depiction, what it means. So the model, so fine-tuning again here, repeating, the model is trained by repeated gradient updates using a large corpus of example tasks. Yeah, this is the standard supervised learning, where, for example, you have pre-trained model, and here you show it an example. Sea otter is okay, who can speak French? How do you pronounce sea otter here? Loutre de mer? Oh, okay, loutre de mer. Anyway, I don't speak French, so pardon my French. Loutre de mer. And then, so you show this example, the training example, and you let the model update update the weights using gradient descent. So after this example, you do the gradient update and change the weights of the model. Standard training. Then you show another example or another batch of examples. Peppermint. How's that? Okay. One. Okay, cool. Something else. Something else in French. And then again, you do the gradient update and so on. So plush giraffe. How's giraffe in English? Giraffe? Giraffe. Plush giraffe. Giraffe peluche. Oh, I love it. This I think I can pronounce that one. So giraffe peluche. Plush. Oh, this is beautiful. Peluche. I love languages. Plush, peluche. Plush. Is in German it's plush as well. Huh? Plüschtier. Plüschtier. Giraffe. How is giraffe peluche in German? Plüschgiraffe. Oh, beautiful. I don't think my daughter has one yet. So, okay. Plüschgiraffe. Gradient update and so on. And then after you train the model, then, well, it learns a task, which is machine translation here, and you just show it a new one. And cheese, so what's going to be translation? Fromage, exactly. Fromage. So. All good. So this is a this is a standard supervised training. So you do the update of the weights after showing examples. Okay, so this is the standard so far. Well, in GPT-3, so GPT-3 was this is just the decoder only model. Decoder only model. So this is what we did last lecture yesterday. So just language modeling thing, just the decoder part. Okay. So they introduced something which they called in-context learning. And what it means, it's the best to be shown on the examples. So there's something which they call zero shot. So you have typically, what does it mean? Like you always say like this is the saying, well, you have just one shot. So one try. You tried once and then you have to fly. Just one shot. Here, this is like, well, you have no chance, zero shot. So I don't show you anything and you should solve the task. So how it works is the model predicts the answer given only a natural language description of the task. No gradient updates are performed. So there's no training in traditional way of the model. The model weights are kept as they are. And what you do is, and again, it's like text in, text out. Everything is text in, everything is text out. You say the model, translate English to French, cheese, and it should give you the answer. So you might be asking, why does that work? Like, how could this actually be possible? Because the model was just pre-trained on the internet, pre-trained in language modeling. It doesn't know anything about translation. Maybe it doesn't know anything about cheese, but it will work. But while it will work, well, it has, yeah.
Have read dictionaries where it's just like cheese translation.
Exactly. There is something in the training data which will help the model to solve something of this task. Not everything, but it has seen the internet, and there's a lot of things in the internet, like bad things, but the good things as well. So it might have seen something where it was a translation cheese and fromage or something like that. So it should be able to predict the fromage. But it's very hard. So zero-shot learning is basically a very hard task because the model doesn't know, might not know anything. I mean, it could be any task. It could be like, oh, translate English to Nepali. Cheese. I don't know why it's Nepali cheese, but maybe GPT knows. I don't know, maybe not. But you didn't show any examples of translation. You didn't even show like what the task is about. So this is zero-shot learning, which means you pre-train your model and you can offer it as an API. And if you use the API endpoint, you can just do the zero-shot learning because there is no update of the gradients. You don't have to, you don't change the model. You don't update the gradients of, gradients, parameters of the model through gradient update. Okay, so this is zero-shot learning. It's very hard because the model has no chance to learn what you want from this model. There is one, maybe we should start here. Should have started here. It's one-shot learning, where you take, you show the task description to the model, and you show the model a single example of the task. So one shot. Okay, here's one shot. Learn this task and then do it, for the new data. And again, there's no gradient updates. No updates of the parameters are done. So again, here we write translate English to French. This is the task description. Then we show an example what we want from. So why are we showing examples where we're trying to mimic how people learn? You show, if you want to teach a human something, maybe you show an example. And humans are good in kind of inferring by examples, but they just need a few. I don't need to show like 100 examples what translation is. I'll show you one. If I show you this, sea otter, loutre de mer, you know like, oh, cheese should be fromage, if you know the task. Right? You just knew, yeah.
GPT translate cheese to Nepali, it answered with the translation for cheese, but in another language.
What? Again?
I asked it for the translation of cheese
Yeah.
into Nepali.
Yeah.
And it came up with a translation. Then I controlled it and Google Translate said something else. But then I inserted the translation GPT gave me and it's cheese, but in Hindi.
Because I guess the script is the same. It's wow, it has a name. Dela Navahari, something like that, and it's the same script as Hindi. Maybe the language is different. I guess it's different, but the writing is maybe almost the same as Hindi. So maybe the cheese is the same in Hindi and in Nepali. Anyway, yeah, okay. So maybe it worked, maybe not. So this is one-shot learning. So you say, well, here's the task. Maybe summarize the document. Then you show, this is the document, this is the summarization, and you prompt it like, okay, here's the new thing. So do it for me. One shot. And it works better somehow. The question is why? We come to that later, but it works. So one shot, you give, well, you show it an example, but there is no gradient update. You don't change the model to perform the task for you. The model keeps frozen pre-trained weights, but you show in context. Why is it called in context learning? Because this is the context, right? I mean, you're giving the model your context, and it learns from this context. So this is why it's called in context learning. No, it's just a term. Somebody label it like that. So in context learning is a thing where you're just basically prompting and showing an example in your prompt. Okay, this is in context learning. And of course, you don't have to have just one shot. You can have a two shot or few shots. So this is the last kind of paradigm. Few shot learning is that, okay, again, you have the task description. The model is shown a few examples of the task. But again, there's no gradient update. So this is the same thing. But basically, you're saying, okay, well, translate English to French is a task. I'll show you a couple of examples. See other, gluten de mer, peppermint, this thing, plush giraffe, giraffe peluche, and cheese is fromage. And of course, what do you think should work like better and what should be worse, like the performance? Any guesses? Like 0 shot, 1 shot, and few shot. What should work best? Few shot, because you're giving more examples. I mean, the more examples you give, it will work better. 0 shot is kind of, wow. If it works, that's a miracle. Well, because it was trained on something in the training data, right? It's not a miracle. There's a reason. But you're giving more chances to show at least one example. So again, we have the standard fine-tuning where you just update the parameters of the model using gradient descent for this task. But now the paradigm has shifted to this sort of prompting, so in context learning, where you have your model frozen. So for example, there is GPT-3. It's super huge. So if you want to train it on your task, good luck. Because it's big, so you need to fit it into your, can you fine-tune GPT-3? People can try, okay, so nowadays, it's easy to fine-tune GPT-2 because you can fit it on your single GPU. Well, you don't have access to GPT-3 because it's somewhere hosted by OpenAI. But if you have like a super huge model like Llama 2, even like fine-tuning Llama 2 or Llama 2, it's complicated. I mean, you cannot do this with large language models because in order to do the parameter update, you need to load the model into memory. If your model is bigger than your memory on GPU, then you need more GPUs. If you need like 4 GPUs to do the training or 8 GPUs for 10 hours, good luck. It's super complicated, like technically. It's really challenging. So not everybody can really fine-tune Llama. So what you do is, well, you can run inference on Llama because it can, you can run it on CPU maybe and do some stuff. Some simplifications, excuse me, which means you can do in-context learning on these large models because you can do the inference locally, or you can just access API. Somebody's hosting the model, and if you can access the API, you can do in-context learning, right? Does that make sense? Okay. So we have these 0 shot, few shot, and 1 shot and few shot. Excuse me. And I think here's some details about the pre-training of GPT-3. I mean, until like GPT-3, there was some details about the pre-training of these models, starting with ChatGPT and GPT-4. OpenAI is closed AI. I mean, there's nothing. So if you read a report about the report on GPT-4, there is one tiny paragraph saying, we don't say anything about training, model architecture, data, blah, 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 nothing. And there's 100 pages of PR bullshit. Okay? So GPT-3 was a little bit different. There is still some information about the pre-training data. So what they used was filtered command crawl. Oh, surprise, surprise. Yeah, of course. You want to take the internet and filter it. And they took some books and Wikipedia and things like that. So, and some mixed them together and blah, blah, blah. There is some information on what is trained, but it was trained on the internet. Let's put it like that. So, and here are some results on, I just picked a couple of those from the GPT-3 technical report, just to highlight the difference between 0 shot, 1 shot, and few shot, and the fine-tuned state of the art. So if you see SOTA, and what is SOTA? It's abbreviation of state of the art, which means something which is the best at the time, and you want to be better than the best of the time. So if you have a new paper and you say like I'm better than state of the art, you're setting the state of the art, like a leaderboard kind of thing. Okay, so what does it mean? Trivia QA. I don't know exactly the task, but it's some sort of question answering, trivia question answering, like who was the first president of the US, something like that. That's what I'm assuming, like, you know, there's details and link to the data in the paper, but it's some sort of question answering. So you have to know the model has to know some knowledge, right? If you need to answer a question like who was this guy or who won the first World Cup, this and that, the model needs to know something about the world. And here, so the fine-tuned SOTA, so fine-tuned state of the art means, yeah, if you take the model and just fine-tune it, doing the gradient updates and the parameter updates, the standard supervised training, that's how you read. So maybe some, 68% accuracy here on this task. Now, there's a couple of different GPT-3 models, from small ones to bigger ones. The larger one has 175 billion parameters. This is like the GPT-3 large, and maybe you have some smaller ones. So what does it show is that, of course, the zero shot, the blue line, is always performing worse than few shot and one shot. Why? Because it's just super hard task. I mean, you just say, translate this, and the model has no idea what you want from it. And if you just show one example, well, the trend is you gain performance. Like even one example gives you boost in every size of the model, gives you boost. This is interesting, right? Of course, if you show multiple instances in your context, like 64, is it few? I don't know, it depends. Yeah, a few dozen shot, let's call it like that. If you show 60 examples, excuse me. Well, the accuracy go up again. Wow, this is interesting. So you have, of course, this is not surprising, because the more examples you show, the more the model learns about the task. What is interesting is the bigger the model gets, the better it works with just one shot or like zero shot. So the largest model, zero shot performance, is actually better than the smaller model performance with few shot learning or one shot learning. Like you make your model bigger, and you don't need any training at all. It will learn, it will do zero shot. It's not as good as fine-tuned state of the art, but what fine-tuned state of the art means, you train your model and your parameters, which means you need the hardware, you need the training labeled data and stuff like that. But here, if you just pre-train your GPT on the internet with language modeling and make it bigger, it will just work out of box. That's cool, actually. That's cool, because the size matters more than your training data or your fine-tuning data. Okay? Here's another example, superglue. Okay. So superglue is the bunch of a collection of language understanding tasks. So a couple of them, some reasoning, entitlement, and all the stuff. And here, okay, well, I think I just made it too big. So sorry. I guess here are the same. The x-axis should be the same as here. So small model up until the largest 175 billions. Excuse me, I didn't pay attention to the detail here. But anyway, the trend is clear. So there is some performance on superglue by humans. So humans don't score 100% because some questions could be hard and humans are just not good enough, or just they don't pay attention. I don't know. So you don't reach like 100% accuracy, or the glue score. If you fine-tune state of the art, you get somewhere close to human. So it's almost perfect. If you have your training data, you can fine-tune your models, and that's great. If you fine-tune BERT large, so the question is like, what was SOTA? I don't know what the model was, but BERT large we know. So BERT large is actually not that great on the superglue. So you have some like 70% score. And also, very important baseline all the time is random guessing. So if you guess randomly what the answer is, you are something around like not 50%, but maybe in this case below 50. And again, so we have zero shot, blue, one shot, and few shot. And so this is a hard task because humans don't score 100%. BERT scored like under 70%, fine-tuned BERT. And the trend is again like from even like one shot, from 0 to 1, there's always an increase in the scores. And if you show like a couple of examples, well, the gain is not that big. But at the end of the day, if you have just one shot with the largest GPT-3 model, and you just show it one example in context learning, it performs the same as fine-tuned large BERT. You know, fine-tuning large BERT, you need training data, you need hardware, you need to run it for a couple of hours maybe on the GPU, while you just take GPT-3 pre-trained, show it one example in the prompt in context learning. Like you just show it in the prompt, you don't do any parameter updates, and it works as well as the fine-tuned BERT. And of course, the bigger the better. Now we see like, oh, a zero shot is actually really hard. So zero shot on superglue, you have no chance. But it's still better than random guessing, okay? So yeah, large model do learn something. But even like with one shot or few shot, wow, it works. In context learning works. Amazing, okay? And now something, well, which is not surprising because we live in the world of ChatGPT, so we know all that. But, you know, 2020, like 4 years ago, before the world knew about ChatGPT and everybody was using that, they try to generate news articles, news articles. And so the largest model, GPT-3, generating news articles. And they ask people whether they are able to identify whether roughly 500 words articles are model generated or not. So whether it's like fake news or no fake news, like it's just the news were generated by GPT or written by a human. And the good news or the bad news, well, people are not able to identify, like to distinguish that. The writing is so good that you cannot tell whether it was written by a human or GPT-3 in this experiment, in this setup, okay? And of course, I mean, can you tell whether an article was written by ChatGPT or not? Well, maybe sometimes says if you're an expert in the domain, but if it's just a news article, well, I don't know. Can you spot it? If you see something like written by ChatGPT, can you tell it's ChatGPT or not? It's an open question. I'm really curious. Like,
there's kind of style to it when it's like a little bit too enthusiastic.
a little bit too enthusiastic, okay?
But I won't say that I can recognize it all the time. But then it has kind of a certain style.
It is a style. Okay, interesting. Depending on what you're asking. Okay, cool.
I can recognize it when it's in an email or a personal message, and it's like very formal. When you ask it to write my coworker and excuse me for being late because I'm ill or whatever.
Yes.
It's like super formal, and I have already gotten some WhatsApps that were generated like this.
Yeah, okay. Yeah, exactly. Yeah, I'm getting tons of emails from, I don't know if I should say publicly on YouTube. I'm receiving a couple of emails from students like which are that long, and they're just saying maybe like yes or no, or can you read this? Or, if you write me an email, just make it short. Don't use ChatGPT, like because I'm just skipping that all the time. I don't care. I mean, I have to like then read it and pick up the information which is important to me. Yeah, so of course. Anyway, but if I read the news articles, I really have no idea. I mean, I really don't know. Sometimes you see like it feels like written by ChatGPT, but sometimes it's like, yeah, who knows? And maybe it's both. Okay, anyway, so this was, but remember, this is 4 years ago. So the world has changed since. And this was GPT-3. Now we have more, powerful models. The crucial question is, why does this work? Why can you put the prompts here and the examples just in the prompt, and it will learn the task better than, it will learn with more examples better, and it will learn with even like zero shot? Why can this work? And to be honest, it's really an active area of research. So there's many things we don't know yet. We have hypotheses, and it's kind of could be like, well, not controversial, but there is no single truth of that. So one example I was just looking up yesterday was this EMNLP paper from the group of Luke Zettelmoyer, so Min et al., the first authors. And they look into that, like, why the heck in GPT-3 the in-context learning work? And they have interesting observation. They say, like, we show that ground truth demonstrations, so ground truth demonstration are the examples we're showing to GPT, like the prompt, like translate, and this is an example, are in fact not required. Randomly replacing labels in the demonstrations barely hurts performance on a range of classification and multi-choice tasks, consistently over 12 different models, including GPT-3, which means something like if you randomly replace this and randomly replace this, it won't do anything, it won't move a needle, it will work maybe like unchanged. So it means like, yeah, that shouldn't be, that's something wrong in there. And what the hypothesis here, instead we find that other aspects of the demonstrations are the key drivers of the end task performance, including the fact they provide a few examples of the label space. So I guess if you show the labels, I mean, that's their hypothesis. If you show the labels, like they do classification, so positive, negative. So you show few labels, and that helps. The distribution of the input text. So you show the example of the input text, not necessarily the end task, like how to solve the task, but you show a couple of examples how the text will look like. And also what's interesting, the overall format of the sequence. So how you type it in, whether it's like one paragraph, two paragraphs, line breaks, semicolon, like the actual formatting of the output plays a role. And actually, just today I saw on Twitter a new paper. Well, every day there's thousands of papers, but that one was interesting, like showing that actually formatting has an impact. So if you screw up the formatting or change the formatting, it will change the results. So if you end up your sentence with 2 white spaces, it will work differently than just one white space. So prompt engineering is a thing, and everybody's trying to do like prompt engineering, and you see all over the places, oh, the best prompts. Learn the best prompts for ChatGPT to improve your performance at work. Here are the 10 tips for best prompts for ChatGPT. So it's all crap. I mean, no, it's good, because what matters here is not that you show the task. There's some little hacks. It might be little hacks or artifacts that the model is picking up and will work better. This is one perspective. Okay, so this is EMNLP 2022. Interesting work with GPT-3 and other models. But there's other more, I would say, like hardcore research on that. And one paper is from ACL this year, ACL findings this year. We explain language models as meta-optimizers and understand in-context learning as implicit fine-tuning. Theoretically, we figure out that transformer attention as a dual form of gradient descent. So it gets very nasty with learning, learning theory and optimization theory and stuff like that. So there is something about it, and this is a really high active area of research, why in-context learning work and why not. And there's different perspectives and different ways of trying things. And one just showing, yeah, actually, if you a little bit shuffle the words, it has some impact and it will work better, and something is important, something not. There's the whole area of prompt engineering out there, and people are trying to sell you like the best prompts and master ChatGPT, blah, blah, blah. Yeah, sure, that will work. Does it tell you something why it works? Not really. And maybe the learning theory people are trying to understand why this in-context learning work, because it might be actually performing something like implicit fine-tuning. So maybe it will do something with changing the predictions such that the weights might resemble the way it was fine-tuned. This is just, and you don't have to know anything of that, but just to show you, like, this is an active area of research. We don't know why it works, but it works. So, and let's finish here a little bit of alignment, instruction tuning, and reinforcement learning from human feedback. So this is really like a last 2 years thing. So, what I have? Okay, Llama 2. Interesting. So one of the latest models, which you can actually download and run inference on, and maybe even like pre-train if you really want. I don't know. is Llama 2, which is a continuation of the paper of Llama 1, which comes from Meta, team at Meta AI or Gen AI at Meta. What's great about Llama is now it's open sourced, which means the trained model you can really download and run it locally, and you can do anything you want. I don't think they show all the training data actually for pre-training Llama. No, they didn't, because they say something in the paper. No, in the paper they say like, we used the internet. But there's other papers actually trying to be more open source, where you actually can download even like the pre-training data. So you can really trying to reproduce the pre-training of these models, including the whole internet which was pre-trained on. And this is what you want, because you want to know like, yeah, does it work because it was seen in the training data or not? And if you don't see the training data, you cannot do anything about it. Like, why it works? It's a magic, or maybe it was in the training data already. But anyway, Llama 2 is one of these models, kind of open sourcing the world. Now it should be also clear why we have the Llama on the Discord channel. You know, there is this tiny Llama icon, so that's why, okay? So everything comes to the end, like there's a happy end. So Llama is one of those like not super, but very large language models. I think decoder based only, which you can download and play around with and do like in context learning experiments. They also introduced something which is in ChatGPT, and this is actually trying to be for the model to be helpful or to behave nicely to you as a partner. So what does it mean? If you write a task, it should solve the task. It shouldn't like start yelling at you or saying like, and it shouldn't like, it should be somehow prone also to, it should be safe. I mean, the whole area of safety of language models is it's a big research area. How to prevent models to, if you ask, well, how do I build a bomb? And it's, okay, number 1, number 2, number 3, yeah. I don't know. I don't know if there's uncensored version of Llama. I don't know. Okay. Okay. Could be. I don't know. So yeah, there could be pre-trained. I'm thinking. I don't know. So I don't know. I would have to double check. But there could be like a pre-train. So there's a thing. You have the pre-training of these models, which is just the next token prediction. If you just do pre-training and then ask it like zero-shot learning, it won't do what you want. It will do maybe some other. I mean, sometimes it will work, sometimes not. You want it to be more task-oriented. So that's why you do like supervised fine-tuning. Okay, well, supervised fine-tuning is nothing else than just create examples, input, output. So here's the first step in Llama or in Llama 2, and I guess in ChatGPT as well, is that you let people, poor people, which we call the annotator, has written both the prompt and its answer. So this is very costly and you don't want to do it unless you're paid by Meta, but I guess they were paying some, some people very poorly anyway. You have to write a prompt, write a poem to help me remember the first 10 elements on the periodic table, giving each element its own line. I mean, okay, I could write this prompt, and I would never like to write this answer. Hydrogen comes first as element number 1. Helium is second for balloons to have fun, and so on. Well, come on, this takes time and money. I mean, this is super costly to write, but they collected a data set of those prompt and response written by humans. Maybe the other, I want you to roast me, I want you to make it particularly brutal, swearing at me. Oh, okay, this is what you don't want from the language model to do. I mean, you might want it, but that's what not OpenAI wants, or Meta, or something like if you put it on, you don't want a Nazi model to be like online. Maybe you want, I don't know. I mean, it really depends what you want. That's why it's called alignment. By the way, alignment means, oh, the model is aligned with people's good needs, or we align with the humanity. This is a buzzword everybody's using. Oh, alignment. We're doing LLM alignment. What does it mean? Well, I don't know. I mean, it's not a technical term. It's not like, yeah, it shouldn't be nasty. Maybe it should be good. It shouldn't tell you like how to become a terrorist. Maybe like, but it's like it's a fuzzy term. Everybody's talking about alignment, but it's a fuzzy term. But it means something like, yeah, it should be somehow good for it shouldn't destroy the world. Which means if you write, I want to roast me, I want to make it particle brutal, swearing at me. So the model should write, I'm sorry, I cannot comply with that request. Using vulgar language or intentionally hurting someone's feelings is never accept blah, 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 blah. That's what you get from ChatGPT if you try something like out of box. So they wrote this, and they also let the people annotate examples of helpfulness. So this is helpful, and this is safe. Okay, this is a safe answer. It's like, no, I don't want to do that. Of course, we know you can hijack the models. If you just do prompt engineering, you try to, you see it all over the place. Like, oh, okay, you can't swear at me. So let's pretend there's a game and a theater, and I'm writing a theater screenplay, and I want two people to argue. Of course. Or can you give me an argument against something very controversial? Like, can you give me argument? So I tried it last week. No, before Christmas. Not last week, yeah. Can you give me arguments about the conflict in Israel? And ChatGPT tells you, no. I mean, this controversial topic, and I can't talk about something. Yeah. I said, okay, cool. I want to prepare my argument, blah, blah, blah. You just rephrase your prompt. Of course, spitting out.
One example where it did this for me was when I wanted to look up a concept for IT security. The first I have a thingy, and I just wanted it to tell me how something works, and it says it doesn't do that because it will teach me to do that thing.
Oh, really? So it doesn't teach IT security because it's a bad thing.
Then I told it my lecture.
Alignment. IT security is a bad thing. Alignment. Okay, we don't want humanity to do IT security.
Yeah,
who decides? Yeah, sorry.
I needed for IT security to learn how to defend systems from such attacks, and then it told me everything.
Yeah, exactly. Who decides what's good, what's bad? That's the thing. Like, it's not somebody is deciding what you should know and what you shouldn't know. And I think most of the cases it's actually good because you don't want to have tools which turns you like easily into a bad guy. But sometimes you need that. So that's why it's not a technical term. It's like it's conceptual thing. Alignment. It's like, yeah, for the humanity. But who decides? Well, the rich West. Silicon Valley decides what's good. I'm not saying it's bad. I'm just, it's objective. Like, the people who are serving these models are taking decisions which are not technical. But it goes down back to like, bias in language models, bias in word embeddings. It's the same thing. You just take the internet and yeah. This is not a lecture about ethics. I do have one. So by the way, I was thinking we might do like guest lectures. I might do one about my research, like my lab's research, but I did have one invited lecture actually in the summer in Darmstadt from Thomas Arnold on ethics of large language models or generative AI ethics. I think we'll do it like that. It's on YouTube, so maybe we'll just use one lecture. I'll tell you like watch this YouTube video because it's very cool, and there's lots of ethics about generative AI. So maybe that could be a way to go because he was talking. Thomas held courses on ethics in Darmstadt for a couple of years, and he gave a really good lecture on that. So we should do that, but not for today. So this is the first thing, fine tuning. So you let people create this. So they focus first on collecting several thousand examples of high quality. SFT means, what is it? SFT, supervised fine tuning. Yeah, why not? Another abbreviation. Why not? SFT, whatever. Fine-tuning data illustrated in the previous table. We found that SFT annotations in the order of tens of thousands was enough to achieve high-quality results. Whatever it means, you somehow measure high-quality results. We stopped annotating SFT after collecting. So, okay, they let people write 27,000 of these pairs. Oh, poor people. Okay, so first, it was super expensive, I guess, and super bad. You don't want to write prompts and answers like you see here. But this is the way how you introduce more, let's say, safety and helpfulness to your model because you want to fine-tune it to be helpful. Okay, so it's pre-trained on next token prediction modeling, but then you want to fine-tune it on something being helpful. So this is the first part. And there's the other part, which is called reinforcement learning with human feedback. So we're not going to go into details how reinforcement learning works because it's not part of the course, but just as a concept, you know that they use that. So the model training procedures applied to fine-tuning, blah, 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 is further aligned with model behavior with human preference and instruction following. So human preference and, okay, they took human preferences and instruction following, whatever it means. The thing is, they collect data that represents empirically sampled human preferences. So human preferences. Okay, so there were humans, where the human annotators select which of two model outputs they prefer. Okay, so this is how it works. So you have the model, you prompt it, or maybe you have two models, or you just prompt it twice because there is some randomness in the output, so you will get two outputs for the same prompt, and you let the human decide which output is better. You say like, yeah.
GPT does it by asking you if it was a good output, and if it wasn't, you can take some down, and then it generates one again and asks you whether it's better or not.
Are you getting paid for that? Why not?
Free and
So welcome. You're part of RLHF for OpenAI, because your feedback matters, and this is how you train on models. You get feedback, which you prefer, which you dislike, and you're helping OpenAI to train better models. That's great.
train better models by just giving it prompts, I guess. So
The prompt is one thing. Yeah, I mean prompts. Okay, you're giving prompts. What do you do with prompts without labels? You add them to your language model, maybe whatever. Okay, but if you give it feedback, what you like, oh, this is a strong signal, because they know, oh, okay, this answer is bad, or this answer wasn't helpful. You're getting feedback. I'm not saying it's a bad thing. I'm just saying like what you do is giving feedback, and you're helping OpenAI to train better models. Is it a good thing, bad thing? I don't know, but that's what you do. They did it even like before setting up, before putting into production. They I guess implemented this in Llama 2 because Llama 2 is more open about what they did. So they sampled this feedback, and they prefer this. Human feedback is subsequently used to train a reward model. So there's another model, reward, which learns pattern in the preferences of the human annotators and can automate preference decisions. Which means whenever you have a couple of different options for your answer, for your prompt, there's a model which ranks them, which one is safer, which one is more helpful, and then gives you the more helpful, more safer model. Here's again. Our annotation procedure proceeds as follows. We ask annotators to first write a prompt, then choose between two sampled model responses. Oh, that's what I said. Okay, so you write a prompt, and the model spits out two outputs because there's some randomness. Why is there randomness in the output, by the way? Why can you get like two different responses for the same prompt? Why there's randomness? You have GPT model, predict the next token. Why is it why you might have like two different responses for the same prompt? Why? Oh, so there's some probability somewhere. So where exactly? You get a probability distribution over what? Over different tokens? Yeah, you're getting somewhere. I mean, that's a good direction. But exactly. So where is the probability distribution? Where does it come from? And why? Where do you get probability distribution over what? And why there is a randomness afterwards? So language modeling, tokens, context, and you're predicting the next token. So what's the probability distribution then? What is it exactly? Yeah? Oh, exactly. Okay, so yeah, we're getting somewhere. It's a probability distribution over your token vocabulary. And it gives you like probability for each token in your token vocabulary. What could be what's the probability of this particular token to follow the context, what of this, of this, of this. So you have a probability distribution over your vocabulary. Right. So there are some tokens which are more likely, there are tokens which are unlikely. So how do you extract the next token from that? How do you generate a token from this probability distribution? Because you get a probability distribution over token vocabulary, you don't get a token. So how do you get it? Okay, highest probability. So you take a token which is a highest probability, and you say like, oh, this is my next token. That's fair. That's called greedy decoding. And it's an important concept, greedy decoding. greedy. You take the most likely, like GREEDY, greedy decoding. You take the most likely token, but maybe that's not the, well, maybe empirically that's not the best thing. So what you're gonna do is actually sample from this distribution, and you add randomness here. You randomly sample from this distribution, and you sample according to the distribution. So which means most likely you will sample the token which has high probability, and unlikely you sample a token which has low probability, but it's a random. And that's where the randomness comes from. You're sampling from this distribution. You can sample from all the tokens. You can say, well, I'm going to sample only from the top 5 tokens. I'm going to sample from top 20 tokens. And top means like with the highest probability. So you can restrict what you're sampling from. But if this is random, real random, then you get randomness, because your token is according to some distribution, but not exactly. It's probably, you're sampling from probability distribution. Sampling from a probability distribution is random by definition. So that's where you get randomness. If you do greedy decoding, you would get the same output every time for the same input, because there's no randomness. You take the most likely one, because you're not sampling, you're taking the most likely. If you're sampling, then there's randomness. Okay, this is the important part. So that's why you get 2 different prompts. Excuse me, 2 different outputs. Oh, we need to hurry up. In order to maximize the diversity, the 2 responses to a given prompt are sampled from 2 different model variants. Okay, variant temperature. Oh, temperature. Okay, we talk about the temperature. The temperature is basically really reshuffling the probability distribution. Like if there's a high temperature, everything will go smaller. If there's small temperature, it will be more spiked. So temperature is a parameter. In addition to giving participants a 4th choice, we also ask annotators to label the degree of which they prefer their chosen response over the alternative. Either their choice is significantly better, better, slightly better. Okay, so you're saying, here's my 2 answers to my prompt. This one is significantly better. Good. Signal. You have prompt, 2 outputs, and signal which one is better. Nice. So that's what I did here, and just very quickly. So collect demonstration data and train a supervised policy. Okay, here's a prompt. Explain, can you read it? It's quite small here. Here it says, explain the moon landing to a 6-year-old. And then the labeler or the annotator demonstrates the desired output behavior. So somebody writes, some people went to the moon, blah, blah, blah. So it's explain the answer. And the data is used to supervise fine-tune GPT-3. Okay, so this is exactly what we had here. So somebody wrote a prompt, and the prompt would be like, oh, describe me landing on the moon like if I were 6, and oh, somebody blah, 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 blah. So this is what you write per hand, and it costs a lot of money, 25,000, 27,000 like this. So you fine tune it, and then the model knows like, oh, okay, I should produce more safe answers, maybe reject some prompts and stuff like that. Then you prompt the model and sample several outputs. So again, the prompt will be the same. Explain the moon landing to a 6-year-old. And we have like A, B, C, D, 4 different answers because they're random, so you can sample 4 different answers. And then the labeler ranks them or makes the preferences. Okay, so the answer B is actually better than answer C, which is better than answer E, and which is better than answer D or something like that. So you basically say, well, yeah, I prefer this one over this one, and you make a comparison, right? I mean, they were using 2 in the previous slide. Here on this example, there are 4 ones, but the principle is the same. And then you use this for train this reward model. So I guess the reward model is something external to GPT. So it's not part of GPT. It's just another model. If you see a prompt and 4 different outputs, you need to learn how to rank them. So it's a ranking model. Okay, which means, so it learns the preferences from humans. And it tries to mimic them. And there's some PPO, so policy optimization coming from reinforcement learning, which we're not going in there like how that works, but it's if you're interested, just look up these papers because it's coming from the reinforcement learning world, which using like completely different terminology and completely different paradigms of learning. We didn't do that, but this is how it works. Like there's 3 steps. One of them is supervised fine tuning. So as we had before, you let people write things, costs a lot of money. Then you let people annotate things. It's cheaper, actually. It's cheaper like to compare because, if you see like 2 outputs, you compare them very quickly, say like this one is better than the other. It's cheap. You don't have to write it. And some people are doing it for free. Like, oh, ChatGPT, I don't like that. Well, everybody's doing it for free. Like, do you give feedback to ChatGPT, like saying it's good or bad? But you do. You say like, oh,
I say
it's possible. Ah, so you didn't do it. Ah, good. Nice, like it. There is no free lunch. I mean, everything you do, like you make somebody more rich. Anyway, and then the second part is then, okay, you learn the preference model, and the third part is how to incorporate the preference model into this generation through this PPO stuff. So this is how, and this is it. This is ChatGPT, this is Llama 2, this is state of the art 2023, 2024. This is the paradigm. So on the bottom, there's a transformer. There's some supervised learning. And what we do is in-context learning because it's just cheap. You don't change any of the parameters. You just do in-context learning. Writing better prompts and prompting. This is it. Now you can build this stuff, get rich, and that's it. Okay, any questions? Good. I hope it was fun. I mean, it wasn't deep, but it was more like high level, current, contemporary LLMs. And there's so many things just being researched, as I said. So as we discussed yesterday, so I don't know what to do next week exactly. We'll do something. So one option could be the ethics lecture, which you will watch on YouTube by your own, so you don't have to come over. That's one option. Is it fine for you? Does it work? Okay. Second option is like the guest lecture. Well, guest lecture. I'll show something what we do in research, like the privacy stuff. Does it sound interesting or not? I mean, if it's fine. I mean, I'm just if it doesn't sound interesting, you have to tell me. Okay, so that's another option. So we have like content for 2 lectures. Maybe we would start with the ethics and then do the other. And how many lectures do we have left? 3? Something like that. And there will be this homeworks checking as well, as we discussed in the last lecture. So yeah, we'll see.